Start.
Yeah, I switched on the recording, so you can start chatting.
Okay. Okay, so before I move on to starting the class today, I'd like to ask you guys if you have any questions from yesterday's class. Did you have a chance to go through any of this? And by any chance, you have any questions? Okay, if you don't have any questions, so let's start with uh, the syllabus for today or the portion for today. So today I will be teaching about IBM Q, how to use IBM Q, and also I will show you a small demo of how to run a program on IBM Q. But I will show a demo using only a composer for some uh, reasons compiling the program and running it on IBM Q doesn't have. I mean, it takes a bit of time, and I cannot guarantee that it will run within the same time we do the class. We can submit a job, but it will take its own time to run and give you an output. That will be like 5 minutes to somewhere between 30 minutes, depending on the queue in the quantum computer. So yesterday I talked with you about qubits, like different realizations of qubits. The three most popular realizations of qubits are superconducting qubits, ion trap based ones, which they call as ion qubits, and the third one is the photonic qubits. Here, photonic qubits are flying qubits, and uh, there is not yet, there's not yet something like a quantum chip using photonic qubits is not in the commercial process, or it's not being used extensively. People are doing it, but it has not attained the level which IBM or Google's superconducting qubits have. So some of the companies which use superconducting qubits are Google, IBM, Rigetti, and Intel. So IBM has something close to 65 qubits in their uh, most important. I mean, the biggest design they have is 65 qubit quantum processor. Similarly, for ion trap qubits, there are two companies. One is IonQ and the other is Honeywell. Honeywell, I think you guys might know, it's a company known for security. I mean, like, what do you call this? Online security features, developing online security features, and so on. Okay, so once you want to learn IBM quantum computer, you need to create an account. The quantum computer is on the cloud, and you can create an account in this cloud using IBM. I mean, you have to go to this website, IBM Q, and you will see this page. Here, you just give sign in or create new account, create an IBM ID here, and what happens is it will ask you to sign up with your email, first name, last name, password, and all these things. I would advise you to sign in with your IITM email ID, because if you sign in with your IITM email ID, you have access to some quantum computers which are not accessible when you use an ordinary Gmail ID. Okay. Once you fill up these basic information,
Chandra,
yeah.
sorry, I should just interrupt. So basically, I suggest that for now they sign in with their Gmail IDs. The IBM, I'm sorry, the IATM account will have to be enabled, and I'll do that by early next week and then alert them. So,
Oh, okay, okay.
to the class, the plan is to have an assignment which is exclusively based on implementing certain things on IBM, and you will upload the final output PDF. Right before the assignment, I'll enable access for all of you via the IITM account. Okay. Yeah.
Okay, so for now, I think you can use the regular Gmail ID and verify your email, and you will come to a screen like this. Okay, So on the leftmost, this arrow, it will give you some news updates. We'll come to that later. On the rightmost thing, this is IBM Quantum Composer. The IBM Quantum Composer is something, it looks like this. Okay, I will explain that in detail later on, but it is like you will be creating the circuit by placing the components in the in a particular place. Okay, then you have IBM Quantum Labs, and if you go to the Quantum Labs, instead of placing the components, you can do write a program which will give you an output. Okay, so if you are going to use the Quantum Labs, I suggest you update or learn Python, because the entire programming is carried out using Python. And it is actually a better idea to use the Quantum Lab rather than the Quantum Composer, because the Quantum Lab, being a programming language, it has many different packages which can be incorporated, and also gives several freedoms in writing a circuit and so on. So whenever you write a program on IBM Quantum Lab, you can actually call a function and you can see the program in the form of a real circuit. So what I mean is, you write a Python code. Okay, there are two options. You can construct a build state using IBM Quantum Composer. Then you go to IBM Quantum Lab and write a Python code for the same build state. Then there is one particular command to show this. Once you use that command, the IBM Quantum Lab will run and show you the circuit as an output, which will actually look very much like the IBM Quantum Composer. Okay. So once you are logged in and you have looked at these, then you will have to understand what these different things are. There are many quantum computers available. For example, can I quickly go? I will quickly go to the quantum. Okay, IBM. This is the IBM web page of my account. So, okay. Result jobs. Okay. Wait. How do I? No. Yeah, dashboard. So this is the dashboard, and it contains all these details. So once you want to look at the circuits and things, you just click here. There are different tabs available here. The first one is the programs. Programs, in the sense, these are very special codes written which you can incorporate, which is freely available for you. For example, the variational quantum eigensolver is a code which will find the minimum eigenvalue of a Hamiltonian. It's usually used to find the ground state of a molecule in quantum chemistry kind of applications. But this eigensolver is available, and you can actually use it or incorporate it in your Python program. Okay. Next, you go to the systems part. The systems will list you the number of will list you some quantum computers. So you have this many quantum computers, but in actual practice, all these things are not available for you. You can see here, it says all systems 23. So there are 23 quantum computers, and it says out of this 23, I can use 9. So these are, if you click your systems, you will see what are the quantum computers available for your usage. You can see there's a single qubit then 5 qubit, 5 qubit, 7 qubit, 5 qubit, and so on. Okay. So once you have that, then you have the simulators. Simulators are not exactly quantum computers. They actually simulate the results of a quantum computer on a regular machine. So there are 5 simulators, and generally you have access to all the 5 simulators. Okay, and on the rightmost side, this points here, actually here they keep updating what are the new things available for use, and if they have any what is the summer Qiskit courses and so on. Okay, and then reservations. There is an option for reserving quantum computer under special circumstances. I don't think we are eligible. I mean, we cannot reserve something right now. But if you have a special account through IITM or something, you will be able to reserve something. Okay. So this is exactly what I showed you before. So it says I've written 5 programs so far, and I have 9 quantum computers and 5 simulators. So you can see that there are 5 simulators starting from 32 qubits to 5,000 qubits. Okay, so the 5,000 and 100 qubits are actually quite good. If you can make use of it, you can solve some real problems on them. But it will still be a simulator. It will not give you exact results like a quantum computer. Okay. So the next point is you have to go to the IBM Quantum Composer and click the Launch Composer button, like here. Oh, sorry. Click that. And then you will come across a screen like this. And here you can see at the top part some little squares with something written inside. And then you have some lines here. This is the circuit part of the quantum computer, this entire box. Okay, and this box here is the program part. So whatever you do in the circuit, it will automatically appear in the program part. So these small little squares here are the quantum gates. So H, for example, H is the Hadamard gate, and this circle with the cross inside is the C0 gate. This is the controlled C0 gate. Oh, sorry, I guess like making a mistake. This is the NOT gate, and this is the controlled C. This is the C0 gate, and this is the double controlled C0 gate. This is a swap gate. This is the identity gate. Similarly, you have all the different gates and things here. So what you can do is you can just drag and drop the Hadamard here. Then, okay, I will have to explain what these lines are. The Q here stands for quantum bit 0, and this for the quantum bit 1. And the C is the classical register. Okay. So if you write something Q0, that will appear as the rightmost part of the qubit. And then if you write Q1, that will be the next one here. For example, okay, let me quickly go to the program and show you this. So I click a new file. Okay, I got this. So you can see that there are 3 qubits. If you want to add one more, you just click on add one more. Okay. And if you do not want, just delete them. That's it. Now, if I want to add a Hadamard gate, let me delete Q1 also. So I have only 1 qubit. Okay. I just drag and drop the H here. Once I dragged and dropped the H, you guys know what a Hadamard does. It takes the state 0 and writes it into 0 plus 1 by root 2. So if you look at it in terms of probabilities, you will have 50% of 0 and 50% of 1, right? So that's exactly what the Hadamard did. And you can see the output here. Okay. Now, I add a different qubit Q1. Okay. So, you can see that the 0 and the 1 is shifted to the rightmost bit. So, whatever is Q0 is the rightmost bit. Q1 is the second in the order of the thing, it's the second bit, and so on. You should remember this notation. Okay. And if I change this Adama, drag and drop it here, you can see that it becomes 0, 0, 1, 0, because the leftmost bit is being changed from 0 to 0 plus 1 by root 2. Okay. So this is how you use it. And let's say the qubit is initially in 0. The beginning, it's always in 0. So, but to be more precise, it's always better to add this 0 kit and then start working with this. Okay. Now, if you want to have one kit, what you will do is add the 0 here and then add. Okay, suppose you want to remove a gate, you just go here and delete the gate. Okay. Or you can add this, and similarly you do the same thing if you want to initialize the state in 1. So you have initialized both the states in 1. That's it. Okay. So if you go here in the file, you can see that there are several options, and I think you can work on this. But there is a very important thing called inspect. Once you click the inspect, you will see a bar here. Okay, and you'll see some arrows here. You click the arrow. The first arrow will tell you what this is, and the corresponding result will be shown here. The second, next, you shift it to this one, and you'll see the result corresponding to it. Then you click it here, and you can see the first one has changed to 1, the first qubit. Okay, and click the thing, and you can see both of them are changed to 1. So what this inspect does is, it tells you, you can click on each element of the circuit, and it tells you what the output of the circuit is up to that particular element. Not for that particular element, it's up to that particular element. If it has 2 steps, it will give you the results of the 2 steps. Then you click it for third step, it will give you the results for the first, second, and the third step. Okay. So this is a very important feature you guys should know, because once you draw a circuit, before you run, you can actually check if you're right using this inspect feature. Okay. So these are the ways to view the output. I will come to it in a little while.
Excuse me, sir.
Yeah,
I have a question.
please.
In that inspect one, right? So
Let me open that up. Yes. Yeah.
so, when you selected Q0 bit, right? So it went to 0, 0.
Yeah.
But 1, 0 state also represent the case when Q0 is 0. Then why 0, 0 as the result is shown here?
Because I have already, no, I've initialized the state here in 0, right? And this state is also initialized in 0, right? Hello?
Yeah, I'm getting.
Because don't worry about this box. Even when you start, this Q1 is initialized in 0. By default, the qubit is always initialized in 0 in IBM Q. Okay. This 0 I am introducing just to be sure it is 0 with very less errors. Okay. So even if I remove this, the answer will not change. It will be the same without these 2 zeros. Okay.
Those are more like references for ourselves, I think, to remind ourselves that these 2 qubits are.
Yeah, except that it introduces some gate times and gate errors and kind of things. Other than that, I think it's better to use this 0 always.
So it's like an initialization, is it?
Initialization. Yes, exactly. Okay. So, okay. Let's get here. Okay. So, the next part is the IBM Quantum Lab. So, once we go to the IBM Quantum Lab, you have these Qiskit notebooks for programming, and then you have other options like markdown files and showing help, contextual help, and all those things. I have never tried, actually, to be honest, I've never tried using these things, but let me see. Yeah, it generally takes a bit of time to load. So meanwhile, so there are two different ways in which the output comes whenever you draw a circuit. One is it gives you in terms of probabilities, and the other is in terms of a Q sphere. In Q sphere means it represents the results on this sphere. Right? Okay, you can change these probabilities to give you state vectors also. So the next thing is we have to, if you click this, it will open some notebook, and oh yeah, it does it. Yeah, you can carry out your programming in this. You can import your different what do we call the packages for Qtip and run them here. And there are several options like selecting cells, and you can run selected parts of the program. It's more like an interactive notebook for Qtip. Sorry, Qiskit. So that's about the IBM Quantum Lab. First, I would advise you guys to first get a hands-on familiarity with Python before you enter into this Qiskit Quantum Lab programming side. Okay. So, out of the available, freely available quantum computers, the one with the maximum number of qubits is IBM Q Sydney. It has something like, I guess, 27 qubits, because you can see it starts from 0 and goes up to 26. And once you have a structure like this, this is, okay, let me, I think it's a little more easier to see it on the real so for example, if you look at it, the ones here with the green dot means it's online. Falcon R4, this is the type of the processor. So the processor design, and the recent ones are the Falcon processors, and some of them and have this tag exploratory, which means it is not yet ready for readily available, but it's like on the experimental stage, not yet completely reliable things. Okay, so IBM Sydney is one of the things which has a large number of qubits and which is readily available. It has 27 qubits, and it has a quantum volume of 32. So I will tell you what quantum volume is in a little bit of time. So this is the architecture of the processor. Here, each circle with a number inside is a qubit, and these lines in between the qubits denote the connections. So qubit 0 is connected only to 1. Qubit 1 is connected to 0, 2, and 4. So that's the way the qubits are connected. It's not possible to do all-to-all connections in these superconducting qubits because of the complexity involved. So they just do some connections, and based on the connections, we can always work out a problem on them. And if you click this, you will see this value 5.091 gigahertz. That is the qubit frequency. So yesterday I told you what a qubit frequency is. It is, if you consider the ground state and the first excited state and find the energy difference, that can be represented as h nu, and from that h nu you can calculate the frequency of the qubit. That is the frequency of light or photonic qubits needed to excite the qubit from the ground to the excited state. Okay, so we have IBM Q Sydney with 27 qubits, and these are the other qubits. We will be getting Montreal, which has really a very good thing. Like if the quantum volume is high, it means it is much more suitable to solve harder quantum problems. The structure looks almost the same. Okay, so go to the next. Okay, and yeah, and also here you will see what are the basic gates available, and the average T1 time and T2 time, which I talked about yesterday. T2 is the decoherence time and T1 is the relaxation time. So when we have our set of, the quantum computers we can use, the minimum is actually we can use the single qubit thing. The maximum we can use is a 7 qubit thing. Using the single qubit thing, you can just do a single qubit gate operations and check them out. That's the thing you can do with them. So these 9 quantum computers fall into 3 different categories in terms of the arrangement of the qubits. So the single qubit machine we neglected, and then we have 6 5 qubit machines and 2 7 qubit machines. The 7 qubit machines have this I-type structure. The 2 machines have this I-type structure, and the 5 qubit machines, there is one machine which has a linear structure like 0 to 1, 1 to 2, 2 to 3, and things. And one machine which has a T-type structure. These are the machines which are available for us. Okay. So when you look at this IBM Q thing, you will always find that the quantum computer is labeled as IBM Q _ and then there's a name. The name depends on the place, the name of a place like Kolkata, Mumbai, Manila, and so on. Then qubits, it shows the number of qubits in the system. And quantum volume. Quantum volume is like the performance of gate-based quantum computers, regardless of their underlying technology. Like if you have different quantum computers, like quantum computer based on superconducting qubits or quantum computers based on ion qubits and all of them are going to work using quantum gates. So you will have to see which one performs better. So there should be some way of measuring it. A quantum volume does that. Okay, it tells you which gate-based computer has what kind of a performance. Okay. Then the system status. Status is it's running or is it somewhat not in operation today and things. Then you have the total queue, number of jobs waiting to be run. And then processor type. Processor type is the one we saw here. That is the topology of the processor and the qubit. What are the qubit parameters and so on. Then services. We have additional information about the system as to whether it can be reserved or whether it supports pulse inputs and so on. I'll tell you about pulse inputs soon. And then, yeah, that's it. Then we'll go back to the quantum circuit part, and you will see this lots of gates. Actually, you will see these squares in different colors, a dark blue. Then there is this what do you call this color? Turquoise blue, then gray, red. So what are these color codes? So the dark blue gates are the classical ones. Then you have the turquoise things, which are the phase gates. For example, T is the Toffoli gate, and so on. Then we have the non-unitary operators given by these gray colored objects. Then Hadamard gate has a separate color for it, which is orange. And then the quantum gates. You have some quantum gates, and these are given through the red or what is this? Red or magenta color thing. Okay. So if you go to this website, you will have a detailed note about what each gate is, and I mean a map from the symbol to the gates you have studied, like, and a brief introduction to, I mean a brief explanation of how to use them. Okay. So these gates, while you see these gates as one square, it's not being implemented in a single step. So generally they use some kind of, it's a couple of steps to implement a quantum gate in the circuit. So this actually, while we might think there is only one gate operation, there is more than one gate operation involved, and there is, because of this, there is some errors and losses in the circuit. To overcome this, there is another idea called pulse gate. Pulse gate is, instead of using these quantum gates, what they have given, we use electromagnetic pulses to simulate gate operations on the superconducting qubits. Okay, for that you can always define a gate with your own name. For example, when you look at let me go to the IBM Composer. You can see this symbol add here. If you click add here, you can actually name an operation. For example, you can name something like invert, and you can create your own NOT gate. And for that NOT gate, you can, what you can do is, you can study the various qubit parameters. You can choose the qubit on which you are going to implement it. And based on the qubit parameters, like the qubit frequency, the T1 time and T2 time, you can give an external pulse, or you can schedule a pulse such that when the pulse acts, there is an inversion happening. Okay. So this is what a pulse gate does. What a pulse gate is, it actually executes logical operations using special pulses. This is like directly working on the qubit, instead of doing a software approach we do in the these kind of gates. But what I would recommend you guys is, first, try everything you have using the regular gates available on IBM Q. Get a very good familiarity on how to use these readily available gates. Then you can start learning pulse gates, and then you can simulate individual gates using pulses. Once you know how to simulate individual gates using pulses, then you can go to the next level of simulating simulating a whole problem using just pulse gates. Like a series of pulses can actually help you in doing a quantum teleportation. You can try to do that. Okay. Okay. Now, finally, there's one more thing we have is Qiskit Metal. Qiskit Metal is a method for quantum device design and analysis. It's open source, community driven, and all those things. And what it does is, you can always design your own transmon, and you can try to run your programs on that. It's more like having a electrical, I mean, when you use electrical circuits in a lab, there are some softwares to simulate the electrical circuits, which can show you what the output can be when for a given input and so on. This is exactly the same thing, but with respect to superconducting qubits. Okay, so there are different things like a design, and then you can make the devices from scratch. Then you can view the device. Then you can analyze the device, suitability of the device. Okay. Now, uh, why this is useful? So this is actually a circuit for a transmon. Okay. So you can see the number of electrical components here is like actually a lot, but you can always figure out the circuit using a you can actually write down the Lagrangian of the circuit and solve it and get the Hamiltonian. Oh, sorry. But this what the circuit is. But in actual practice, what they do is they take a silicon substrate and etch these components on the substrate. When they etch these components, they have to create the effects of having a capacitor or an inductor. So this is what a etched surface, etched super transmon looks like. This is actually a design of an actual transmon which will work. Picture B is the design of an actual transmon which will work. So using this Qiskit metal, what we can do is we can write down 4 transmons. We can draw these 4 transmons. Actually, even within this transmon, you can actually individually draw each one of these blocks. You can actually set the spacing here, and you can see this one is a connector wire and there is a read wire, and you can actually design each one of them. Okay. Then you can design a path, which is the coplanar waveguide, for taking microwave qubits from one superconducting qubit to the other. So there are 4 paths, and then once you have drawn the path, you can check how it will work in this circuit. So let's say you make a simple mistake. For example, you are trying to connect this lead to this lead, and you want to go through this path. If you drop it vertically down, and if it touches this, then there's going to be electrical short and this circuit will not work. So in these cases, Qiskit Metal will tell you that this point you have an error, and you have to change it so that there is no short in the circuit. So you can just draw this line and it will go in this path. Okay. Yeah. So thank you for this, but the class is not yet over. I will quickly show you the Bell state and how to do it. So, okay. So we have a Bell state 0, 0 plus 1, 1. Okay. If we want to construct the Bell state, what we have to do is, first let us initialize both the qubits in the 0 state, 0 and 0. Then we put a Hadamard gate in front of this first qubit, and then a C0 gate, control C0 gate. Then we do a measurement on the first qubit and the second qubit. Okay. Now I want to run this. So I will set up and run. So once you set up and run, here you have an option to choose the different quantum computers or these simulators. Okay. First, let us see if we can run it on a simulator. So I don't know if I never used a simulator before, but let's say Bell simulator. So it's running. So after some time, dated, so we got a job result. You see this new job result. And we go here to see the result. You can see that we have a state 0, 0 plus 1, 1. 50% outcome in 0, 0 and 50% outcome in 1, 1. Please note this point. We have an exact 50% in each 0, 0 and 1, 1. This is definitely not what we will get if we run it on a quantum computer. So let us choose a quantum computer. Let's choose something which has less pending jobs, like this one, no pending jobs. So Bell, let me call it as Bell 5. Okay, now I run this here. So it is running. We go to the jobs page and we can see it is running. Give it a couple of minutes, and in the meanwhile, let's see if we have see more details. If you go to see more details, okay, we got the job result for this as well. So let's go to the jobs, and yeah, Bell 5 is also completed. And you can see that 0, 0 and 1, 1 are present here, but you will see a small frequency, small outcome for 0, 1 and 1, 0, because you will not have a perfect result on a quantum computer. It's a probabilistic thing, and you will have a small probability of 0, 1 and 1, 0 appearing. So let's see, click see more details on this. So if you go to the Bell simulator, we will have just the circuit, and then we have something called the transpiled circuit. Transpiled circuit is something which means if you implement a circuit on the composer, it gets converted into a machine usable form, and that's the transpiled circuit. Okay, you can see that there is no difference between these two in the simulator. Okay, next you can actually download these circuit diagrams as PDF or PNG files and save them. So when you are given what is your problem sheets, and when you solve these things, we want you to draw the circuit and then download the PDF and include this in your Word file or a PDF file in which you are giving the results. Okay, so that's the way for us to check. So here you can see the frequency of 0, 0 is actually a little higher than 50%. 1, 1 is lower than 50%, and these two guys are a little more than 0. Okay, now this is the actual circuit we drew, and this is the circuit we have. So if we have given 0 and 0 here, so it ignores it because the states are already initialized in 0. Now when we have this Hadamard here, a Hadamard is implemented using a RZ Rootex and RZ gates actually, and then the control node is implemented as a control node. So you can see that the transpiled circuit here actually has more elements than the actual circuit, because the Hadamard is not implemented as one single gate. It is implemented as a series of gates, which gives you the result of a Hadamard. Okay. So compare this with the simulator. It will be exactly the Hadamard, because in the simulator you don't have a circuit. It just it gives an output corresponding to the circuit which you have drawn. Okay. So again, once you have these things, you can measure. This is the measurement in the Z basis, which I didn't tell you, but okay. If you go to this, you can see the program in QASM, and if you you can do it also in Qiskit Python. Okay. So this is the way you actually do the build state. Anything else left? I don't think I have anything else to say on this. Yeah. So the first task I would advise you to do is practice using all these gates. I think it will take you a couple of days to use these gates and actually relate them with what you learned in your theory class. Relate them with what you learned in the theory class and practice using them. And then try to solve for a Bell state. Creating one Bell state is actually easy. Try to create all the Bell states. It'll require a bit of thinking, but I think it's very easy to do. Okay. Okay. So I think that's the end of the class. So do you guys have any questions up to this?
Any questions? Okay, so then all of you will create accounts for yourselves using Gmail first, explore the different aspects that Chandra has covered today, and you'll be all set to do an assignment next week, right?
Yeah, I forgot to add one thing, Prabha. There's a
Yeah.
very good Qiskit documentation available online from the same Qiskit. Just type Qiskit documentation on the web. It's prepared by the team which has created IBM Q. So that documentation, read this documentation parallelly when you're working with that. Okay, it gives very much required details which are not present anywhere else.
Yeah, I think there's a kind of full tutorial on this, right? And
Not just a tutorial, it's like it even tells you like these ways of how these gates, for example, this Hadamard is not a single operation on
correct.
composer. It's a series of operations.
Right.
So sometimes when you have to look at the gate timings and the gate or reduce the gate operations, what kinds of gate you have to remove and what kinds of gate you can use. That's actually, those kind of things are discussed there.
Right.
And always look at the transpiled circuit when you do it. Main circuit is okay, you drew this, but transpiled is the main thing. Yeah, there's a question. So the small errors is not due to the transpiled circuit. It's because when you do any quantum mechanical or quantum information theory things, there's always going to be a probability that you're not going to prepare the state exactly in what you want. That's giving you these errors. This will happen even when you do an experiment. For example, when you do a quantum optics experiment and try to create a Bell state, and you will create a Bell state, and then you can do a tomography to see the Bell state. When you do the tomography, it will give the different probabilities of existence of the elements like 0, 0, 0, 1, and so on in terms of bar diagrams. You will see that even the ones which you did not target for will appear, because when you create, there will always be some errors in state creation. Okay.
Chandra, this is not just the state creation, right? So I think is also getting confused by the fact that the transpiled circuit does not have the ket 0, ket 1. See, that doesn't make so much of a difference. It's more the fact that there are
That
errors in the
0 and
gate
1.
implementation, right? There are also errors in the
errors in the gate implementation. There are several steps of errors actually. Yeah.
See, Hadamard is not a single operation like Chandra showed, right? In the transpiled circuit, it's actually it's a sequence of 3 gates. You're decomposing it as 2 rotations. So remember in class, we discussed how every gate can be broken down into a sequence of rotations. And I said the rotations are native to the IBM architecture. So it's that sequence followed by the C naught. The C naught has its share of errors. right? So this combination of errors is what finally leads to the fact that you don't have a perfect bed
Exactly.
state. So it is not just the initialization. Initialization also could be faulty. On
Yeah.
top of that, there could be errors in the gates also. And maybe in IBM, the C0 is also somewhat noisy, right?
Yeah, actually, C0 is the most noisy thing, I guess, because
Right.
they measure their IBM gate timing in terms of C0 gates. They want to keep it minimal. Try to avoid C0 as less as possible. Okay,
Yeah.
Manoj, in edge gate operation, there are errors. Like we are not ruling that out for Manoj's question. And for Siddharth, yeah. Okay, I showed you two things. One is the using the IBM quantum simulator. The simulator does not use real qubits. Okay. Then I used another thing, which is the IBM quantum computer, which came with IBM Q underscore name of some place. Like I think we used Manila, or not Manila, Jakarta. Okay, that is a real IBM qubit. So that's the difference. That's why when you had a simulator, your results were perfect. But when you had a real quantum computer, it is not that perfect.
Yeah, so whenever you're doing something on the simulator, it's basically being simulated on classical hardware.
Yes.
So they do have, like I think Chandra also showed, they have these different kinds of simulators also, and they have noisy simulators where in the classical simulation itself, you can incorporate, you can try to mimic the real qubit by putting in the noise in the qubits, in the gates, etc. But those of you who have worked with this, or the experience has been that the actual run will be much noisier than even the noisy simulator, right? That's usually the case, unless you have a very small circuit, right?
Okay. So once you guys are familiar with using the composer, I will advise you to go for a programming approach. Like composer is for fun and trying to learn. Get into the programming approach for real-time things. Okay. And then start learning what are the different packages available. Like you have packages to simulate external end noises, environmental noise like decoherence, phase flip, bit flip, and all those things. How to include them, how to correct them. There are a lot of things you can try out. Even with these 7 qubits, I think there are hundreds of problems and examples you can try out. And I would like to tell you that it will be a lot more fun doing those things. Okay. So, yeah.
Yeah, indeed. I mean, if everything is perfect, then yes, we have like a perfect quantum computer. So the errors have nothing to do with the inherent theory of it. I mean, it has nothing to do with the fact that these are quantum bits, because as we've discussed, the unitary circuits are very much deterministic operations, right? So if I put a Hadamard and a C0 and I put a 0, 0, I should get a 0, 0 plus 1, 1 by root 2. That's what the theory tells me. So it has nothing to do with the randomness that comes from quantum mechanics. That only affects, if you have a measurement at the end, then the outcome is probabilistic. But this error is due to the fact that your qubits themselves are not stable. They suffer something called decoherence, which Chandra explained yesterday also, relaxation and decoherence. And the gates also have errors. And in the time that you implement, so like you said, the C0 takes the longest to implement perhaps, right? And so in the time that it takes to run these pulses, your qubit state itself would have undergone some change, on top of which the gate operation is also faulty. So anyway, there is a whole theory built on top of this called quantum error correction, and on top of that, fault tolerant quantum error correction, where the idea is that if you somehow manage to keep these errors below some threshold value, then you can still get a pretty good, pretty high fidelity outcome, right? That your outcome will be very close to the ideal one if you keep the errors below some threshold. So that's still work in progress, right?
Actually, these superconducting qubits they have a good fidelity. Like in the order of 95 to 96, I guess, right, Prabha? Like in
Their qubits themselves, yes. And also, I think the gates are also mostly good, except for the C naught. Like you said, the C naught is still noisy. Whereas if you go for something like ion trap, I think the C naught has very high fidelity in an ion trap. And that's a big advantage of the ion trap that.
yeah. Ion trap actually has a much higher fidelity, like 99, I guess, is their
Correct.
fidelity. They have a better,
Yeah.
yeah.
But the ion trap problem is that your qubits are kind of glued in place. Like, you have to get connectivity and to get them to talk and do circuits is much harder. It's somewhat easier with superconducting qubits. So every architecture has its.
Yeah, there are limitations, and actually, what I find is with experimentalist qubits are like religion. Everyone likes their own. But one of the interesting things to watch out in the future is the photonic qubits. Now, people are trying to make processors out of photonic qubits. They are trying, and if it works out, there are two advantages. One is it will work at room temperature, and the second will be like it is mostly with optical components, and yeah, mostly with optical components, and the fidelity is also will be like you can actually compare it with at least the superconducting qubit fidelity, or even a little more than that. It will be between ion trap and superconducting qubits in terms of fidelities, but doing them would be very easy.
Yeah. And maybe in room temperature is a big advantage. Yeah.
Yeah. And it doesn't need a special even environment, because qubits rarely interact with the environment, so they don't get defaced that easily.
Right.
So we can relax on that aspect. We can be assured that it's not going to deface so fast. Does quantum volume represent how less the errors are? I think it's not about how less the errors are. It tells you the capacity of the superconducting qubit in solving a problem. In some sense, it depends on the qubit architecture. In some sense, it depends on the interqubit, the qubit frequencies and decoherence times and all those things. It's a whole set of, it takes in a lot of factors, and tells you how better one processor is when compared to others. It's like a scale for comparing processors.
So
And there
I
are
think
many
there are
factors
a bunch
involved.
of inputs that go into it, Sunit. One is the errors, and there are two kinds of errors. Like I said, one is the qubit itself, its coherence time, right? The second, the T1, T2, both times. Then the gates and their fidelities. And the third is the connectivity also. So in some sense, it seems to capture how large a quantum circuit you can run with the least amount of error.
Not it allow. I think it also takes into account the qubit frequencies, Prabha. Like when you have something like 7 qubits, not all of them are going to be in the same frequency range, the same frequency value, right? They are going to be in a range of frequency. How narrow that range is,
Okay. Yeah.
because you need to send the microwave qubit from, let's say, qubit A to B. If qubit A operates at 5.3 gigahertz, qubit B can operate at 5.4, and you can set a small detuning and let the microwave communicate with each other, like let them talk through microwaves. And if qubit B is like 7 plus or something, then the microwave used in A will be totally useless in B.
Right. So it's also then about addressability, like how easy you can address and
Addressability.
get
Yeah,
this
there are a lot of factors in it actually.
right. So it's a somewhat comprehensive method.
Yeah. In fact, when they make these superconducting qubits, it's etched, but it's not perfect up to the millimeter. That's what brings in these small changes in the qubit frequency. It's not at the level of printing exactly the same circuit. That thing is not yet there, I guess.
Right.
You can do that in electronics.
Yeah. So I think I think that's a fair statement to make what Sunita said, that the higher the volume, the larger and more complex. See, it's not
Surely.
just complex, it's also the size. See, complex also means how many qubits have to talk to each other. So we'll maybe in a couple of weeks look at the quantum Fourier transform circuit, and then you realize the level of connectivity that you need is very high. So it's both the things. It's depth and breadth, as they say. Both the aspects of the circuit will go into the complexity. And yes, I think you can say that higher the volume, the more complex circuit it can handle. Right?
Yeah. Hello.
Yeah, Chandra. Can
Oh
hear you.
yeah, I lost. I think I lost your voice for a second. Okay. Okay, Prabha. So I
Yeah,
think
thanks,
we
Chandra.
can finish the class today. Yeah.
Yes,
Thank you.
yes. Yeah, we've gone well beyond time. So thanks, Chandra. And this recording will also be up on.
Yeah, I will send you the slide and the note right away. So slide, today's slide and yesterday's notes right away. Okay.
Okay, thanks.
Okay, Prabha.